Alright, this is the second video of 11th week, and from this video, let me move on to chapter 11. So we go back to optimization problems. So in the previous chapter, we studied two transcendental functions and how to take the derivative down. The scope of functions we can take the derivative of gets larger and larger. So now with those advanced techniques, we go back to optimization, okay? So in this chapter, we extend the basic optimization theory we studied in chapter 9 to function of several variables. So the main objective and the main target in this chapter is, so now we are going to study how to find the relative maximum mean of this kind of function. So when function depends on several variables, okay? So chapter 11 is a little bit lengthy, so I subdivide the chapter into two pieces. So in this video, let me introduce the relevant theory, and in the next video, I'm going to show you several examples, okay? So let me start with some motivating example. Why we should be able to deal with this kind of optimization problem. So, when function depends on several variables. Think about conglomerates. Such a firm produces not just a single product, but several different products. If you think about Apple's, Apple produces not just iPhones, but several other computers, say MacBook or tablet PC in the name of iPad. Okay, so such a firm may be interested in what is the most efficient production plan. So in the sense that it minimizes production cost. Okay, so the related question can be written as given cost function. So if the firm produces two different products, then the firm has to decide the output level of each product, say product one and product two. So the associated cost function will depend on two variables, okay? And the most efficient production plan, Q1 and Q2, will be the solution to this optimization problem. So we will encounter this kind of optimization problems several times when we study economics, okay? So that optimization problem appears in economic context, very naturally. So we should know how to deal with that, okay? So I'm gonna start with a theory for functions with two choice variables, okay? So in most times we focus on functions with two choice variables, just as this function. So f depends on only two variables, and we are gonna study how to find the largest or smallest value of this function, okay? And it turns out that this theory is readily generalized into multivariate functions. So when function depends on more than two variables, okay? All right, so to start, let me go over the basic optimization theory we studied in chapter 9. So if we have a function depending on just one variable, okay? So the function is given by z equals f of x. And if this function attains an extreme value at some point x star, we know this function must have zero derivative at that point. That was the first order condition, okay? So that fact is illustrated by this graph. So we have the graph of one arbitrary function, and this function has a local max at point b prime. Okay, so the slope of the tangent line is equal to 0, and a local mean at point b. So the tangent line is horizontal. So the derivative must be 0 at this point. Okay, at these two extreme values. So if so at point A, the function is decreasing at this moment. So derivative is a negative. So if we increase the value of x, so when dx is a positive, the function is decreasing. So this is not a minimum value. And if dx is a negative, so we slightly reduce the size of x, and the function is increasing. So it's not a local maximum either. Okay. At point A, the derivative is a positive, meaning that function is increasing in this neighborhood. If we increase dx, so if we increase the size of x, then the function is increasing, so not a local max. If we reduce the size of x, then function is decreasing, so it's not a local mean either, okay? So this is the necessary condition for extreme value, okay? But this is not sufficient, but a necessary condition, because if we take a look at point C, at this point, the tangent line is also horizontal. So derivative is equal to 0, but this is neither local max nor local min. This is an inflection point, right? So the curvature of the function is changing at this point, but this is not an extreme value. So the function was a concave, right? When x does not reach the point C, but after this point, the function starts being convex, okay? So at the inflection point, the curvature of the function changes, but that is not regarded as local max or local min. Okay? So that suggests that we have to examine the sign of the second derivative to classify whether we have a local max or min at that critical point. So at point B prime, the second derivative is a negative, so the function is concave. The graph of the function is bent downward like this. And at point B, at this point, the second derivative will be positive. So the convex, or the graph of the function, is bent upward. Okay? So that is what we studied in chapter 9. Now we attempt to extend this theory to multivariate function. Okay? But unfortunately, this derivative test does not work because when function depends on several variables, we have several derivatives, right? So when function depends on x and y, we have two partial derivatives. So at the very first glance, it is unclear with which derivative we have to work. We may have to work with partial with respect to x, or the other partial derivative, so partial with respect to y. So we have to modify this derivative test, okay? But the basic idea comes from differential. So one comparative advantage of this differential is in contrast with the derivative, because in case of a single variable, derivative is uniquely determined. This single function has only one derivative and then only one second derivative, right? But in case of several variables, we have several different derivatives, partial derivatives. Okay, but differential is uniformly applied to every function irrespective of the dimension. So irrespective of the number of variables. So we can find the differential for this function, single variable function, in the same manner, in the exactly same manner. We can find the total differential for this function. So when function depends on several variables, okay? So this differential has the same definition for every type of function, no matter what the dimension is. So that is a one comparative advantage of this differential compared with the derivative. So we are going to modify this derivative test to differential version, okay? But that is a piece of cake because there is a close relationship between derivative and differential. So if you think about the derivative, so derivative can be written as dz over dx. If we call the output z, then the derivative is going to be the ratio of the two differentials. Okay, so marginal change in z over marginal change in x. Okay, so we can rewrite this in terms of differential. dz equals f prime dx. Okay? So remember, the derivative specifies the linear relationship between these two differentials. Okay, so at extreme value, we know that derivative boils down to 0. Okay, so no matter what this dx is, we can state the first order condition, dz equal to 0. So equivalent condition in terms of the differential is dz equal to 0. Okay. And if you think about the second derivative, so second derivative was written by d squared z. So second order total differential divided by dx squared. That is a f double prime, the derivative of the derivative. Okay, so we can write the second differential d squared z as the second derivative times dx squared. Okay, but if you think about dx squared, that is a marginal change in x squared. So if we increase x, so x is a positive, but if we reduce the size of x, so if we decrease x, so x is negative, no matter what the sign is, x squared is always positive. So dx squared is always positive. Okay? So the change in x squared is always positive. So, but the derivative test requires at a local max, second derivative be negative, at a local mean be positive. So the sign of the second order differential, d squared z, will be governed by the sign of the second derivative. Right? So when second derivative is negative, this guy is also negative. When second positive, this guy will be positive. Okay, so we can restate the second order condition for extreme value as so the second order differential is a negative at a local max but positive at a local mean. Okay, so that is kind of equivalent condition to the derivative test. But the advantage of this is it can be directly applied to multivariate functions. All right, so the derivative test can be couched in terms of the differential. So now using this, we study how to find the local max or local mean when function depends on two variables. Okay, so we can start with the first order condition, differential version of the first order condition. So set dz equal to 0. Okay, but we know how to find the total differential for this type of function. So that's going to be partial with respect to x times dx plus partial with respect to y times dy. Okay? So the first of the condition requires that this expression, so total differential, be equal to 0 for every marginal change, so for every pair of dx and dy. So the equivalent condition to this one, so for this equation to hold for every pair of dx and dy, so for every marginal change in x and y, the coefficient f sub x and f sub y should be equal to 0. Okay? If one of them is a positive or negative, then you can easily find that dx or dy, this equation does not hold. Okay? So at that value, this equation does not hold. So the equivalent condition to this one is two partial derivatives are equal to 0. Okay? Using the gradient, remember the gradient is defined as, so that is nothing but the collection of partial derivatives. So when function depends on two variables, we have two tuple vector. So that is the gradient of function f. So f sub x and f sub y. So that should be equal to 0 vector. Okay? So we can state the same condition in three different ways in terms of differential, and in terms of partial derivatives, and in terms of the gradient. Okay? But they are three equivalent conditions. Okay? They indicate the same thing. If you think about geometric interpretation of this condition, and I have two graphs here. So, when function depends on two variables, the graph of the function will be surface in the three-dimensional space. Okay? So we have z-axis, x-axis, and y-axis. And the graph of this function has a local max. So from this graph, we can see that the function has a local max, actually global max at point A. So f sub x is equal to 0 implies that the tangent line tx parallel to the xz plane. So if you think about this tangent line passing through point A, so that is a tangent to the graph of the function at point A. Okay, so that has a zero slope. Okay, so along this tangent line, notice that uh, the variable y is held constant. Okay, so that is consistent with the definition of f sub x. When we compute the partial with respect to x, we treat the other variable y as a constant. Okay, and treating x as the only variable. But along this axis, so along this tangent line, that is parallel to the x-axis. So along this axis, only variable x changes and y is held constant. Okay? So f sub x is equal to 0 implies that this tangent line has a zero slope. Okay? And similarly, f sub y equal to 0 implies that the tangent line t sub y, now this guy, that is parallel to the zy plane. Okay? So where the variable x is held constant. Okay? On this plane, on zy plane, x is fixed. Okay? So that line is parallel to y-axis. So along this axis or along this tangent line, the value of x is a constant. Okay? It's fixed by constant. So f sub y is equal to means, so in this partial derivative, x is fixed. X is a constant. That means, this tangent line has zero slope. Okay. So if the function has an extreme value at some point, then the two crossing tangent lines have zero slope. That is implied by this first order condition. Okay. And at this point, in this graph, function has a global minimum at point B. Okay. And the condition is the same. So the two crossing tangent lines must have a zero slope at that point. But this first order condition is not sufficient condition, but necessary condition. So we already discussed this case, or this possibility, when we studied the single variable function. So the counterexample was y equals x cubed. For this function, derivative is 3x squared. So that will be 0 at x at the origin. But if you think about the graph of the function, it looks like this. Right? So the curvature of the function will be changed at the origin. So that is an inflection point. But the function does not have extreme value at this point. So although derivative is equal to 0 at the origin, so the slope of the tangent line is equal to 0, the function does not have any extreme value at that point. So for this reason, first order condition is not a sufficient condition for extreme value. Okay, so we have to check on the second order condition. Okay, so in case of multivariate functions, we do have the same point. So multivariate function may have inflection point. So that possibility is illustrated by this graph. So at point D, the function has an inflection point. So it's a little bit tricky to, so how to approach this graph, but if you see, so if you take a look at this graph at this angle, okay? So if you project this graph onto zy plane, okay, then you're gonna get this graph. Okay, so at point D, the slope of the tangent line, so the tangent line parallel to zy plane, that is a t sub y, has zero slope. Okay, so curvature is changed, but the function does not have any extreme value at this point. But if you take a look at from the other angle, so from this angle, if you project this graph onto zx plane, then you're going to get this graph. Okay? Once again, at point D, nothing happens. The function is monotonely increasing. Okay? So we don't have any extreme point at point D. So that can be regarded as the inflection point when function depends on two variables. Okay? But in addition to inflection point, we have another point in multivariate functions. That is a saddle point. Okay? So saddle point is illustrated by this graph. So if you think about the graph of this function, it looks like a saddle. We usually put on horses. Okay? So at point C, if we think about the point C, the two crossing tangent lines have zero slope. But at this point, nothing occurs. This is not a extreme value point because if we look at this graph at this angle, okay, then the graph looks like this one. It has a U shape. So at point C, we have a global minimum. Yeah? But from this angle, so you project this graph on zx plane, and it has so now it is overturned. It has a upside down U shape. So at point C, the function achieves global maximum. Right? So one salient feature of the saddle point is this. So at that point, we have a local max along one axis. So along the y-axis here, meaning that we change y only. So given x, given a fixed value of x, we change the value of y only. Then the graph of the function has this U shape. So at point C, we have a local minimum. Along the crossing axis, so now we change the value of x only. Okay? So now the function has an upside down U shape or hump shape. So at point C, the function has a local max. Okay? So one salient feature of the saddle point is, depending on the angle, we can regard this point as a local max or local min. Okay? So that's why we often refer to saddle point as min-max point, okay, or max-min point. It can be seen as a maximum from one angle, but from the other angle can be seen as a minimum. Okay. All right. Okay. So anyhow, in order to find the local max or min, when function depends on several variables, we have to look up the second order condition. Okay, so we have to develop the second order condition, sufficient condition. Okay, so we must look to the second order total differential d squared z. Okay, so remember the differential version of the test. So d squared z must be negative at a local max, but positive at a local min. Okay? But that is related to the second partial derivatives. Okay? So the partial derivative of the partial derivative. When function depends on two variables, x and y, it has a total of 4 second partial derivatives. Okay? So it has two first order partial derivatives, f sub x and f sub y, depending on the choice of our variable. Okay, so here f sub x, we choose x, and y is regarded as a constant. Here f sub y, we choose variable y, and x is held constant. Okay, and so depending on the choice, we can make another two partial derivatives, f sub xx, f sub xy, and f sub yx, and f sub yy. Okay, so the last node means here f sub yy means we start from this function f sub y, okay, And still regarding y as a variable, we take the derivative. Then we obtain f sub yy. For this guy, f sub xy, we start from, so that is inherited from f sub x. So we start from f sub x. Okay? Regarding this as a function of x and y. Okay? And then treating y as a variable and x as a constant. And then take the derivative. Then we obtain f sub xy. Okay? So we have a total four second partial derivatives. Right? So f sub xx means, okay, we start from f sub x, the first order partial derivative. Okay? And then we take the partial with the same variable one more time. That is f sub double x. So the notation is, remember for the partial derivative, we use curly d. So curly d squared f divided by curly x squared. And similarly, f sub yy, we take the partial with respect to the same variable twice. Okay, so this guy, given this guy, we take the derivative with respect to the same variable to obtain this. Okay, f sub double y. Okay, and f sub xy. Okay, that is, we start from partial with respect to x. Okay, so we first take the derivative, partial derivative for y. Okay, but in the second, now we change the variable. Now y is the variable. So we take the partial with respect to y. Okay, and we obtain second partial with respect to x and with respect to y. Okay, because we took partial with respect to x first, so this curly dx comes first, and then curly dy comes next. Okay? And now we switch the order f sub yx, so we start from this partial, and then take the derivative, partial derivative with respect to x. Okay? Then we obtain curly d squared f and curly dy and curly dx. Okay? So the only difference is we start from taking partial with respect to y. Okay? That is a switched version of this. So total we have four partial second partial derivatives. So we have two double partial derivatives and two cross partial derivatives. Okay? You can easily see that if function depends on three variables, x, y, z, okay, then, we have three partial first order partial derivative, f sub x, f sub y, and f sub z. Then each gives rise to three different second order partial derivatives, f sub xx, f sub xy, f sub xz, and f sub yx, f sub yy, f sub yz, f sub zx, f sub zy, f sub zz. Okay? So we have a total 9 partial or second partial derivatives. When function depends on four variables, we have a total 16 second partial derivatives, and so on. Okay, so it grows the number of second partial derivatives grows exponentially. All right, so in case of 2, we have 4 second partial derivatives. But here is one important fact. Although f sub xy and f sub yx are treated separately, they have identical values. So these two cross partials look different, right? Because, in this case, in this partial, we took the derivative with respect to x first, and then y next. Okay, here we switch the order, okay? But does not matter. You know what? These two guys are equal to each other in a very general condition, and that is known as Young's theorem. Okay, so this theorem tells us under very general condition. So when function is twice differentiable, and then the two cross partials are continuous, but you don't have to care about that. In our class, the every function we are going to deal with has this property. Okay, so under very general conditions, we have f sub xy equal to f sub yx. So these two cross partials are equal to each other at every point a comma b in the domain. All right, so although it seems that we have four partial derivatives, the last two are equal to each other. So we have three. Okay? So in other words, the differentiation order, okay, does not matter. Okay, it does not matter. We took the derivative with respect to x first or y first. Okay, the two cross partials are identical. So let me show you some examples. So here we have function z depending on x and y, and we have two first order partial derivative f sub x and f sub y. So f sub x is going to be 3x squared plus 5y. Okay, so x is a variable, so 5y are constants. So that will be here. And then x will be gone. The derivative of x is equal to 1. Okay, so we have 5y. I guess you are now familiar with this partial derivative. And f sub y is 5x minus 2y. Then we take the derivative one more time. So we start with f sub xx. Okay, still x is a variable, y is a constant. Then take the derivative, and we obtain 6x. F sub xy. Now x is a constant, y is a variable. So we start from here, f sub x, and take the partial with respect to y. Okay, so x is a constant, y is a variable. So we obtain 5. Okay, f sub yx. Okay, now we start from here. X is a variable, y is a constant. So we have 5. And note that these two cross partials are equal to each other. This is not a coincidence. That is a special example of Young's theorem. Okay? And finally, f sub yy. Okay? So y is a variable, x is a constant, and then derivative is negative 2. And then one more example. So now it involves natural exponential function. Remember, the derivative of natural exponential so it has its own derivative. So it does not change at all. But we have a negative sign in the exponent. So e to the power negative y, whose derivative is, so we rewrite this function and then multiply by the derivative of the power, so negative 1. Okay, so negative e to the power negative 1 is the derivative of e to the power negative 1. Okay? Okay, so with that in mind, if we compute two partial derivatives, f sub x and f sub y, first order partial derivative, and f sub x is going to be, so e to the minus y is a constant, so 2x e to the power minus y. F sub y, now x squared is a constant, okay? So leave it alone, and minus x squared e to the power minus y. Okay. Then the second partial derivatives, f sub xx, okay? E to the minus y is a constant, okay? So x becomes 1. We have 2 e to the power minus y, f sub xy. Now 2x are constants, okay? So minus 2x e to the power minus y. F sub yx, so we start from here, okay? So now we work with this function, treating x as a variable, y is a constant. This guy is a constant. So minus 2x e to the power negative y. So once again, these two are equal to each other. They have the same expressions. Okay? Always, as in this class, always. Okay? Okay? So f sub y, finally. So we took the derivative one more time with respect to y. Okay? So we have one more negative sign. The only thing changes is so we have one more negative sign, so the sign becomes positive. X squared e to the power minus 1. Okay. So this is the uh, way to compute second order partial derivatives. Okay? So now we are going to find out what is the second order condition for extreme values when function has two choice variables. Okay. So once again, we have to figure out the sign of the second order differential, d squared z. Okay. When this is a positive, when this is a negative. Okay. So we first obtain the expression of d squared z, so second order total differential. Okay. So for this purpose, we apply the definition of differential to dz. Okay, so d squared z is a differential for dz. Okay, but dz is right here. This is right here. So z is given by f of x and y. Okay, so dz is going to be f sub x. That is a function of x and y. And dx plus f sub y. That is a function of x and y, dy. Okay, just as partial derivatives can be regarded as a function of x and y, right? So these two partial f sub x and f sub y are functions of x and y. Okay, so we take differential one more time. Okay, so following the definition, if we take the differential one more time, then that is going to be the partial derivative of dz with respect to x times dx. Okay, that was so for general function g, say we have a function g of x and y. So its total differential is g sub x dx, g sub y dy. Okay, so now we regard dz as a function of x and y. Okay, and we have to put first the partial with respect to x, and then multiply by dx, and then partial with respect to y times dy. Okay, but dz is right here. Okay, if we take the partial with respect to x one more time, then f sub x becomes f sub xx, and f sub y becomes f sub yx. But by Young's theorem, f sub yx is equal to f sub xy. The order of taking differential or taking the derivative does not matter. Okay? So we have f sub xy dy, and multiply by dx. Okay, and then going back to dz, now we take the partial with respect to y, and f sub x becomes f sub xy, and f sub y becomes f sub yy. Okay, so we have this, and then distributing dx and dy, you will obtain this expression. Okay, and if we take a look at this expression, the last expression, regarding dx and dy as variables, and the degree of each term, the degree of the first term, there is a 2. Degree of the second, here is 1, and here is 1, so total 2. And degree of the last, there is 2. So every term has degree 2. So this sort of polynomial is called quadratic form in mathematics. Okay, so when function depends on just one variable, quadratic form is like a 3x squared or 1/2 x squared, right? But when function depends on two variables, quadratic form looks like 3x squared plus 5xy minus y squared. Okay? We have two variables, but each term has degree 2. X squared, that is 2. X and y, 1 plus 1, 2. Y squared, degree is 2. Okay? So this kind of expression is called the quadratic form. Okay? Going back to second total differential, it takes a quadratic form regarding dx as a variable and dy as another variable. Okay? And it takes a quadratic form. Okay? So now we are going to take a detour, okay, and to study the main properties of this quadratic form, because now so we are trying to figure out when this second differential is positive or negative. When this is positive, we know the function attains a local mean. When negative, function attains a local max. So the remaining question is when this second differential is positive or negative. Okay. So for this end, to this end, we are going to take a detour and study this quadratic form for a second. Okay. So the quadratic form looks like this. Okay. So some coefficient x squared and another coefficient xy and another coefficient yx and another coefficient y squared. Okay. Of course, x, y, and yx are the same. So we can rewrite this a11 x squared, a12 plus a21 xy plus a sub 22 y squared. Okay. Once again, x and y, so degree of each term is equal to 2. Right? And remarkably, this function can be put as the product of three matrices. Okay. Now we go back to the matrix class. So the quadratic form can be written as so if we have this quadratic form, for example, 5x squared minus 10xy plus y squared, that can be written as xy, and the coefficient of x squared comes first. Okay, that's going to be first entry in this matrix, in the middle. And the coefficient of y squared is going to be the last entry. Okay, and then off diagonal entries, we have some degree of freedom here. We have negative 10 for xy. Okay, so we may assign negative 9 and negative 1, or negative 8, negative 2, and vice versa, or negative 5 and negative 5. So any two entries whose sum is equal to negative 10 give us the same expression. Okay? And lastly, we have xy. Okay? And notice that this is a 1 by 2 matrix, and this is a 2 by 2 matrix, and this is a 2 by 1. Right? So by the rule of multiplication, these are cancelled. So we are left with 1 by 1. That is a scalar. That is a number. And this quadratic equation is a number. Okay? So we end up with the same expression. Okay? So so we have some degree of freedom on the choice of off-diagonal entries. But we want to make this one, so we want to make this matrix be symmetric. Okay? So we have two identical off-diagonal entries. But that can be easily achieved because so we have a sub 1, 2 plus a sub 2, 1 for xy. Okay? So the way to make the middle matrix, so the matrix in the middle, be symmetric. So if B is equal to a sub 1, 2 plus a sub 2, 1 divided by 2. Okay? Just as I chose negative 5 here, I had negative 10. Okay? So if I equally assign to each entry and negative 5 and negative 5, then I can make this matrix be symmetric. Right? So, any quadratic form can be represented by the matrix, symmetric matrix. Okay? So quadratic form will take a form of, so in terms of matrices, if I call xy, so this xy, so 2 by 1 matrix, matrix X, okay, so I use the same letter, so it might be a little bit confusing, but yeah, so that this is a variable matrix, okay? Then this 1 by 2 matrix can be written as X transpose, okay? Interchanging row and column. So this 2 by 1 matrix, after taking transpose, becomes 1 by 2 matrix, right? And then let me call the matrix in the middle matrix A, okay? Some coefficient matrix, okay? So quadratic form can be put as the product of these three matrices, right? So that is a one feature, one interesting feature of this quadratic form, okay? So now we examine this quadratic form for a second, okay? And then going back to second order condition. So if we think about the value of the quadratic form, depends regarding this as a function of x. Okay, now x is a vector or matrix, so it has two variables x and y. Okay, when x and y are equal to 0, in other words, this matrix is a zero matrix. So when x and y are equal to 0, then no matter what this inside A, okay, no matter what these coefficients, regardless, we are going to have 0. Okay? So the quadratic form takes on the value 0 at the 0 matrix. So that is not that interesting. So that is always true. So always takes the value of 0 at the 0 matrix. What is interesting is, what is the value of this quadratic form at non-zero matrices? Okay, so when x is not equal to 0, okay, so what is the set of values this quadratic form takes at non-zero matrices? And intuitively, that depends on the characteristic of the matrix A inside, right? So think about this AX cubed. So it can be put as XY. Okay, so if I choose the inside matrix 1, 0, 0, 0, then you can easily compute that this multiplication product that is going to be so not 1 but 8. And you can easily see that this is 8x cubed. Okay, so depending on the sign of A, if A is a negative, then no matter what x, this guy gives us negative value. If A is a positive, it gives us positive value. Okay. If we take a look at the second, x squared plus y squared, its matrix form is going to be, now we have a identity matrix in the middle. Okay. And the resulting expression of this is going to be x squared plus y squared. But in this case, no matter what x and y, this gives me positive value. Okay, and finally for the last one, and the inside the matrix is going to be -1 and 2. We have 2 for xy, so equally divide that number. So assign 1 and 1 to these two off diagonal entries, and then we can make that symmetric. Right? So at the first glance, it's not that immediate whether this function is positive or negative. Right? So when x is large, due to this negative sign, we may have a negative value. But when x is small, we may have a positive value. So now, depending on x and y, this guy, this quadratic form can take a negative value or positive value. Okay? Remember, we want to, all discussions is for determination of this quadratic form, the sign of this quadratic form, whether that is a positive or negative. Okay, so we are looking for conditions under which this second differential is a negative value or positive value. Okay, so the sign of this expression, quadratic form, depends on the characteristic of the matrix inside. Okay, and specifically, we call that symmetric matrix A inside positive definite if the quadratic form is always positive for all non-zero matrices. Okay, no matter what x, okay, so no matter what value of x, this variable x and variable y, we have a positive value, just like this one. So 1, 0, 0, 1 identity matrix is a positive definite. Okay, and then we say matrix A inside negative definite if the associated quadratic form is always negative. Okay, for all non-zero matrices. Of course, when X is a zero matrix, we know the quadratic form is going to be zero. That boils down to zero. Okay, so we only consider non-zero matrices. Okay? And finally, if for some value of some matrices X, quadratic form is a positive, and for some other it is negative, we say that matrix is indefinite. Okay? Indefinite. And now we are looking for conditions under which this symmetric matrix is positive definite or negative definite, or it is a undetermined, indefinite, right? That shows up in the next slide. Okay? So once again, we have two variable quadratic form, ax squared, 2bxy, cy squared. It can be written as in terms of matrices like this. Okay? Coefficient of x squared comes first, and coefficient of y squared, is going to be the last entry, and we have 2b. Okay, so that is half will be off diagonal entry. Right, and then let me call the matrix in the middle matrix A. Okay, and it turns out that symmetric matrix A is positive definite, meaning that no matter what x and y, we have this quadratic form. So this expression is always positive if the matrix inside, so the first entry A is a positive, and plus AC minus B squared. So A times C minus B squared is a positive. So A times C, this quantity, minus B squared is positive. Then matrix A is a positive definite. And when A is negative definite, if leading entry is a negative, and AC minus B squared is a positive. So when leading coefficient A is negative, but AC minus B squared is a positive, we have negative definite. So this quadratic form always takes a negative value. Okay? And in other cases, for example, A is positive, but AC minus B squared is negative. Or A is negative, and AC minus B squared is also negative. So in these two cases, symmetric matrix A is indefinite, meaning that this quadratic form can take a positive or negative value, depending on x and y. Alright, so using that, we can easily determine the given quadratic form is positive or negative definite. So whether that takes a positive value or negative value. So now I use the other variables u and v, but does not matter. It is a quadratic form. Every term has degree 2. So its matrix form is uv 5, 2, and 3 halves, 3 halves. Okay, and then uv. Okay, so the leading entry is a positive. And then AC minus B squared. So A times C, 10 minus 3 halves squared, that is a positive. So it falls into this class, this case, right? So, the symmetric matrix, this guy, is positive definite. So that means quadratic form is a positive definite. So it takes a positive value no matter what u and v. All right. Okay. So now let me extend this theory to n by n symmetric matrix. Okay. So you may observe that this AC minus B squared is a determinant of this 2 by 2 matrix. Okay. So A is this first entry. Okay. Then AC minus B squared, this quantity is a determinant of this 2 by 2. So if we have an n by n matrix, say, this 3 by 3 matrix, how do we know quadratic form associated with this matrix? Remember, one symmetric matrix gives us one symmetric form. If the matrix is given by this, and by pre-multiplying xy and post-multiplying xy is transpose, we can make a quadratic form. So one symmetric matrix represents one quadratic form. So every quadratic form can be represented by one symmetric matrix. Okay? So we can think of associated quadratic form for this symmetric matrix. Okay? So now we have three variables, x, y, z, and x, y, z. Okay? And you can easily check that the product of these three matrices gives us quadratic form. Every term has degree 2. Okay? So it's going to be x squared, something x squared plus some coefficient xy and xz and yx and sorry, not yx, not yz, yz and y squared and z squared. Okay? I don't know the exact coefficient, but its quadratic form has 1, 2, 3, 4, 5, 6, 6 terms. And every term has a degree 2. So how do you know this quadratic form takes a positive value or negative value, no matter what x, y, z? Okay? So the way to figure it out is, now in case of n by n, if all leading principal minors are positive, then symmetric matrix is positive definite. And I briefly mentioned leading principal minors in the previous class a long time ago, but just remind you of this definition. If we have an n by n matrix, okay, the first leading principal minor is this one, Q11, okay, the very first entry. And the second leading principal minor is defined by determinant of this 2 by 2. Okay? So this 2 by 2 inside the blue box. And the third leading principal minor is going to be the determinant of this 3 by 3 matrix inside the yellow box, and so on. Okay? So if all leading principal minors, so the determinant have a positive value, and the symmetric matrix is positive definite. Okay? So going back to this 2 by 2 case, the A can be regarded as the first leading principal minor. AC minus B squared, the second leading principal minors, right? Because we have just 2 by 2, so it ends right here. Okay? So every principal minor is positive, and matrix A is a positive definite. Okay? And the second, if it's all the principal minors are negative and even principal minors are positive, then matrix is going to be negative definite. So delta 1, the first principal minor, odd number, negative. Delta 2, second, even number, positive. third minor, 3, odd number, negative, and so on. So if the sign of the principal minors alternates like this, okay, so it starts from negative value because the first one is odd number, right? So negative, positive, negative, positive. If the sign alternates like this, then the symmetry matrix is negative definite. Okay, so here we have two by two case. The first one negative, second positive. Then matrix A is going to be negative definite. All right. So in 3 by 3 case, so the first leading coefficient or the first leading minor 2 positive. The second 2 times 10 minus 9, that is positive. The last one. Now we have to do some algebraic work. So let me choose, say, first column, 230. Yeah, let me leave it for exercise. This you can easily check that this is going to be positive. So every leading principal minor are positive. So this matrix A is a positive definite. Okay? So finally, we go back to second order differential. So that takes, it has this expression, quadratic form. So in terms of matrices, we can rewrite this as this. Okay? Dx squared coefficient, that comes first. And then dy squared coefficient, f sub yy, that comes the last. Okay? And we have two f sub xy. Okay? So we have f sub xy as a off-diagonal entry. Right? So we want to know when this is always positive, no matter what dx and dy. Okay? So when d squared is a positive, the matrix inside is a positive definite. Okay? So for function, this matrix consisting of second partial derivative is called Hessian matrix of function f. Okay? So f sub xx, xy, xy, yy is called the Hessian matrix. Okay? So if the inside matrix, Hessian matrix, is a positive definite, the equivalent condition is the first leading minor, f sub xx, is positive. Okay? And then the second, f sub xx, f sub yy, minus f sub xy squared is positive. If all minors are positive, we know the matrix is a positive definite. That means its quadratic form is always positive. Okay? And if the matrix is a negative definite, so f sub xx is negative, but the determinant f sub xy squared is positive. And we know when sign alternates like this, the matrix is negative definite. Okay? In this case, regardless of dx and dy, okay, this quadratic form, in other words, second differential is negative. Okay? Now we can summarize our discussion as follows. So if the function depends on 2 or 3 or, no matter what, no matter how many, so, however, so does not matter, the number of variables, okay? The first order condition for maximum, local maximum, the gradient or partial derivatives for dz should be equal to 0, okay? But the second order condition is d squared z must be negative, right? Must be negative for local max, meaning that some Hessian matrix H must be negative definite. Okay, so when function depends on two variables, the condition can be written this way. Okay. For local minimum, we have the same first order condition, so the gradient or partial derivatives or dz should be equal to 0. Okay. But for second order condition, now Hessian matrix must be positive definite. So in this case, we have a positive second total differential. So according to the differential version of derivative test, or differential version of optimization condition, we know at that point a function attains local minimum, right? So I guess this video might be a little bit boring and tedious because we discussed the theory only, but in the next video, let me show you several examples, okay? So I hope you guys enjoyed this video, then I will see you in the next.